Okay, Neil, we can see you coming down the ladder now.
Our next phase of exploration is go to Mars. Humans would visit, but only briefly, maybe 15, 30 days, and then a year goes by before the next crew arrives.
That isn't collapsed too far, but if that...
Deeper into space, say Mars, the site is so far away that sending people there from the very beginning to inhabit that site just is going to be cost prohibitive. And it's not really necessary if we have the robotics and autonomous technology to take care of the systems when the people are gone.
That's one small step for man, one giant leap for mankind.
A biped walking machine.
Our world-leading algorithms are one of the reasons why NASA came to us in terms of being able to control this complex platform.
So when we're watching humanoid robots moving, we consider this motion very easy, very simple. In fact, it is a lot harder to get them to move like a human than it looks. For example, the Now robot, all that we have done here is to make the robot look like it moves like a human, but we have designed its body specifically to make it easy to control. The Now robot has feet specifically designed to be bigger to help it balance. It's designed in proportion so that it does not fall over that easily. Its mass distribution, its weight, is close to the feet. This is called the base of support. If you compare that to a human, we people are sort of heavier on the top, have small feet, our center of mass is quite high.
When you are standing, you're making subtle movements with your waist that are adjusting your center of gravity over your feet. So this is a challenge for us. As we were thinking about biped locomotion, we recognized that kind of mid-body torso mechanism was going to be very important. So the torso that we built from the very beginning had to have a narrow and thin waist joint that could move left and right and fore and aft, which is essential for balancing your CG over your feet.
A key aspect to understanding environment is understanding the semantics. What is the meaning of different objects? The Now robot cannot do that. So what I'm doing here is I'm trying to get the robot to move from one pose to another pose, like doing a keyframe animation of a puppet. So once I have the sequence done, the robot will just blindly follow this. What the Now robot is not doing is having an awareness of what its environment, reacting actively to what's happening around it, and trying to balance itself actively and use its environment to move around. With Valkyrie, we are breaking a new ground. We are trying to build a machine with an awareness of its environment and then combine this with motion planning and real-time control so that we can make a machine which has the ability to make decisions like humans would. It's no longer enough to just make the robot look like a human. It needs to also behave like a human.
So along with all the sensing and state estimation challenges, one of the things that we have to constantly address and try to achieve is the form factor of these computing machineries.
So in the context of a human, the main resource for doing computing is the brain, which is only about 1.4 kilogram and about 15 centimeters long. When a supercomputer requires about 15 megawatt of power, a human brain 20 watt of power. A supercomputer requires several floors of a building. A human brain is just enclosed in a tiny box of about 15 centimeter cube.
There are algorithms out there which can do visual servoing and tracking of complex objects, but typically they use very high-end computing, large GPU clusters, and if you think about autonomous robotic platforms which have to be pretty self-sufficient in terms of enclosing all of its compute power within its body and not have an umbilical cord, then we have to work within the limits of the compute power that is afforded by this platform. And that is a big challenge. We need to write special algorithms, special code to deal with that.
Asimo is different from now. If we give it an input, if we give it a grid-like map, it can then adapt its motion and plan the motion around this so that it will seemingly react to what's around it.
Now that you're up there, can you show us how to come down the stairs? Motion planning in the current state of the art deals with high-dimensional systems in an offline fashion, meaning you have a system, you compute with it for a long time, and then you put a solution, you wait for the robot to execute it, and then look at the result, and then replan again and move. Oops. Well, actually, Asimo first needs to simply, precisely calculate its position to be absolutely sure that it's safe to come down, and that's exactly what he's doing right now. So it's a sort of, you're sort of interleaving this step of planning, acting, and pausing all the time. Asimo, are you ready now? Okay, on you go.
The machine looks like it's dancing and it's responding to the music, but what it's not doing, it's not able to perceive and update its map as it's moving through the environment. If, for example, there was a table in the middle of the stage, Asimo would not be able to then figure out how to move around it because it does not have the sensing capability. Similarly to the now, it is just following a pre-programmed sequence. Asimo is one step closer to a human than a now. If we give it the pre-programmed parameters, it can adapt itself to it, but it's still nowhere near the capabilities that people have.
If you want to coordinate joints to realize a particular movement that is synchronized in terms of stability, energy efficiency, and obstacle avoidance, you don't want to bump into things. Motion planning in high-dimensional systems is a very hard and still unsolved problem in the domain of robotics, in the domain of machine learning, in the domain of mathematics.
We humans process over 400 billion bits of information in every second. We coordinate over 200 joints. We calculate and recalculate our trajectories. We do real-time control. Of course, as humans, we don't consciously do any computations. Our brains do the math for us. There are currently no machines that can do this.
Humanoid robotics is at the top end of that spectrum. We've got multiple degrees of freedom or joints. So for a humanoid of the kind that Valkyrie is, it's about 44 degrees of freedom.
Lots of different force torque sensors at the ankles, different pressure sensors at the soles of the feet, different springiness in the soles of the feet. And as we start walking in soft soil and start climbing on more irregular surfaces. But the kind of multi-point balance being worked on here at Edinburgh is going to be really important for the future of robots in space.
When we have such high-dimensional systems or high-dimensional robots with 44 degrees of freedom or joints, then from a mathematical point of view, it is hard because the solutions to these kind of problems lives in very high-dimensional space.
So look at how dancers move. They are very dynamic, fluid, precise, fully in control. With Valkyrie, this means 500 calculations a second. This obviously puts a strain on the CPU, on the memory, on all parts of the system, because we have to deliver 500 calculations per second.
Searching in those spaces is a computationally hard problem.
If we don't do these calculations right, we can have a loss of battery, we can have a motor failure, we can place our feet in the wrong position, we can lose balance.
We need very efficient methods that are speedy, have the right representation, and use some tricks of physics to actually establish what is the right bias to apply.
They say that a journey of 1,000 miles starts with a single step. You can think of the first step to have been with Leonardo da Vinci's Mechanical Knight. Da Vinci started asking questions about the human physiology. How do our body moves? What are our degrees of freedom and how our muscles move our body around. And these are still the questions we ask in robotics now when we are building humanoid robots.
Our focus is doing work.
If Valkyrie is going to do work on Mars, can't have any pre-programmed maps, we can't have any pre-programmed inputs or any pre-programmed motion plans. Everything has to be spontaneous and computed on the spot. Now, this is exciting new research.
This robot is definitely working hard